Okay, perhaps we can start. So I think I will start. So likely you can see me. So I am pleased to welcome you in the airport session in this SESAR Innovation Day 2020. It will be my pleasure to introduce our two speakers later. So let me first quickly introduce myself. My name is Bruno Lamiscar. I am the scientific director of Neometris. After some some time, let's say, spent in other organizations like Onera in Toulouse or INAC, also in Toulouse. I think in the program is a little bit mistake saying I belong to ST2A organization. ST2A is a project actually. We currently have with Neometis and ENAC under the KTN Catalyst scheme, and it's related to flight centric ATC with Airstreams. And we have a poster, gives me the opportunity to make some advertising on that. So that's done. So this is my pleasure now to introduce our first speaker, Jan Elver. So Jan is a research associate and a PhD student in the transport engineering at the Institute of Aviation and Logistics in the Technical University of Dresden. His PhD project is entitled Stochastic Control of Airline Ground Operation in a Hub Network. It's supported by the SESAR Engage ATM. And Jan was graduated from the University of Lugano in Switzerland with a master's degree in transport economics, and then completed his bachelor studies in industrial engineering and management at the Technical University of Dresden. His main field of interest are airline operation, operational research, process analytics, and simulation. And Jan will present his paper entitled Development of Stochastic Delay from Cost Function. And Jan, the floor is yours.
Thank you.
And welcome to this presentation on the development of stochastic delay cost functions, with which we want to predict delay propagation under uncertainty for tactical airline schedule recovery. My name is Jan Efler, and I'm very happy to present to you today the results of a study that we have conducted at TU Dresden in the course of my PhD project, with the valuable support of Andrew Cook from the University of Westminster. I have structured my presentation in 5 chapters. I will start with a motivation and the objective of my entire PhD project, then continue with an introduction into our schedule recovery model, then present to you the methodology for this article, which we have applied in a case study. The motivation for our research activities on ground operations at TU Dresden are that the turnaround is actually the biggest primary delay contributor, as was recently confirmed by the performance review report of Eurocontrol for the year 2019, where we can see that more than 30% of departure delays are attributed to the turnaround. Which brings us to our working hypothesis that we see this huge impact from the turnaround arising because of a lack of ATFM and airline cooperation and coordination, meaning that especially in the case of deviations to the initial schedule, there are different paradigms involved for the evaluation of individual flights. So we know, for example, that for ATFM, each flight is equal when they impose capacity regulations based on the first planned, first served principle. And in contrast for that, for airlines, each flight is unique because they have to constantly synchronize their individual network layers, such as ground operations, which involves the consideration of airport constraints and the available resources at an airport, then the aircraft routing with the assignment of tails to the individual flights, the crew pairings, where some crews are changing between individual aircraft at an airport, and the most complex layer, which involves the passenger origin and destination products, meaning that passengers are changing between flights at an hub airport. So the objective of my PhD project, and this study is a part of it, is to develop a decision support algorithm for airline ground operations, which can consider the complex schedule recovery trade-offs within an airline network under uncertainty. If we can see here within this rather small example, which contains just 5 parallel turnarounds, that there are already a lot of interdependencies among the individual turnaround sub-processes. And if on top of this we consider a deviation from the initial schedule, such as an inbound delay, this delay might propagate in different directions within this network of sub-processes, such that we need to assess various trade-offs. First of all, along the aircraft rotation. So do we need to delay an aircraft with inbound delay also on the outbound side, or can we apply some turnaround recovery options? And secondly, along the passenger and crew transfer connections towards other aircraft, which may cause non-rotational reactionary delay, because we would need to delay also these aircraft to maintain the passenger and crew connections. Otherwise, we would incur cost of rebooking, care, or compensation. With this slide, I briefly want to introduce to you the underlying schedule recovery model for airline ground operations, which we have already developed at our chair. Thereby, according to our understanding, schedule recovery seeks to regain feasibility and performance within an airline network, which means that we do not necessarily need to maintain the initial schedule, but we can rebuild it in order to regain feasibility and performance. To accomplish that, we have applied an extended version of the resource-constrained project scheduling problem, and our objective is to minimize total cost incurred by delays and schedule recovery. There are some basic constraints that need to be considered, which are typical for a resource-constrained project scheduling problem. And the first one is that all the turnarounds can only be scheduled after the estimated in-block times of all the aircraft. Then all the processes which surpass the scheduled off-block times are recorded as delay. Then the delay is distributed over several segments, and each segment is bounded. And once the delay in this segment surpasses the upper bound, there are some event-related costs which are triggered, which I will explain you on the next slides. Furthermore, there are some precedence constraints between the individual turnaround sub-processes, as I've shown you on the previous slides, and they can only be neglected once there is a recovery option applied. The actual model is much more complex and involves all of those listed recovery options that we can see here. If you are interested in how we modeled these constraints, that I would like to refer you to an article which is in the last stages prior to publication, and once it's coming up you can read all the precedence constraints that we have modeled in there. As we have seen on the previous slide, delay costs are directly represented as a parameter in the objective function, and therein are compared against schedule recovery cost. And hereby it is important to consider flight-specific delay cost in order to improve the solution generation process. Because if we would consider the reference cost of delay, which have been determined statistically for various aircraft types by Cook and Tanner, and we would need to recover a situation with two similar aircraft types, this would be rather fuzzy, because we would assume identical cost functions for both aircraft and then compare them against the cost of a respective recovery option. And if then the resources to enable this recovery option are limited, it's hard to decide which flight should be given priority. On the other side, if we would have two flight-specific delay cost functions, it is easier to make the trade-off, as aircraft 2 has only a smaller amount of delay that can be accepted before it's more efficient to apply the recovery option to this aircraft. Another benefit of these flight-specific delay cost functions is that we can consider network effects that appear in downstream operations. And for this study, we have assumed some delay costs to be linear, such as additional crew rage or passenger dissatisfaction. But there are also some event-related delay cost drivers which only appear once, but then they cause sudden cost rises, as we can see on the left. Such events might be that a passenger is missing his or her connection at the destination airport and then needs to be rebooked or compensated. Another event-related cost driver would be that a crew is falling out of its duty time, or that because of a night curfew a flight needs to be cancelled. And we can see that these step cost functions are substantially different to the reference delay cost functions that have been defined by Cook and Tanner for various aircraft types. And the final benefit of flight-specific delay cost functions is that we can consider uncertainties comprised in downstream operations, and with this we can predict the probability of delay propagation. So the big question is how to build those stochastic delay cost functions. And the first thing that we need to consider thereby about such a sharp step linear cost function that we see at the bottom left is that it assumes static block times, meaning that an outbound delay at the hub airport is directly propagated as inbound delay towards an outstation, also meaning that the cost of the inbound delay at the outstation can be counted back as cost of outbound delay towards the hub. However, we also know that block times itself are not static, but that they follow stochastic probability density functions. So that for a given outbound delay, for example, as we can see at the bottom here for 20, 25 or 30 minutes, there are different probability functions that the outbound delay causes a certain amount of inbound delay at the outstation. So in some cases the delay can be compensated during the flights, sometimes it remains the same, and sometimes we collect even additional delay during the flight. So that the cost of inbound delay at the outstation, which we know from the blue curve, need to be integrated with the probability density functions of the respective outbound delay category. And as we see, as the result of this integration, we can see that the sharp step linear cost function is smoothed, and we obtain this stochastic delay cost function. And of course, every flight has different stochastic block time parameters, which we can learn from historical flight data. For some flights, we have actual block times which overrun the scheduled periods, so that we can see a dislocation of the smoothed cost function towards the left. And some flights have additional buffer times comprised in their scheduled block times, so that we can see a dislocation towards the right. And then we typically see for short-haul flights that there is less variance in the probability density function of the inbound delay at the outstation, as we can see in the middle figure, which results in a closer fit of the stochastic function in relation to the step linear cost function. To the contrary, if we observe long-haul flights, we typically have more block time variance, so that the stochastic delay cost function is straightened out and has a wider fit in comparison to the step linear cost function. And of course, we have also a combination of all those effects, so that, for example, for smaller delays, we have less variance, and for higher delay, we have more variance, so that the step linear cost function is distorted according to these effects, and then we have a combination of all effects into our stochastic cost functions. We have implemented the step linear and stochastic delay cost functions into our schedule recovery model in order to compare the calculated optimal recovery decisions. The model was then applied to a case study setting with 15 aircraft of one airline which has its hub at Frankfurt Airport. We can see here the flight plan and the initial stand allocation, which have been adapted from a day during the summer season 2019. The aircraft have been selected according to their respective inbound and outbound flights, so that the case study covers destination in typical airport clusters of this airline network. For example, we needed airports of or hub airports of partner airlines, because at such airports our passengers might transfer onto other flights. And then we have other airports with high frequency on the respective route and low frequency on the respective route, just because to model the difference that with high frequencies there are more options to rebook passengers onto future flights, and thus we need to pay lower compensation according to regulation 261. To the contrary, if there's low frequency, there's lower options to rebook the passengers, and with this there might be also higher final arrival delay at the final destination, and thus we have to pay higher compensation to our passengers. Within this case study environment, we have then introduced a scenario situation with an estimated average arrival delay of almost 20 minutes. And we can see here in the flight plan the individual delays of all the 15 aircraft. And on top of this baseline delay situation, we have added increasing inbound delay for aircraft 13 to make a sensitivity analysis of our recovery solutions. And why we have chosen aircraft 13 to be this causal aircraft, I want to show you in detail on the next slide. As you can see here, after the turnaround in Frankfurt, aircraft 13 is scheduled to fly to Stockholm Arlanda and directly returns to Frankfurt afterwards. In the blue lane, we can further see that there is some block time buffer on each flight leg, and that upon the return to Frankfurt, the aircraft has a maintenance event scheduled with some buffer time that it must not miss. In the magenta lane, we can read that the crew flies the entire cycle with the aircraft, and there are no critical duty time restrictions that need to be considered. In the green lanes, we see different passenger groups. First of all, those passengers flying to Arlanda, from which some continue on to other flights and have different connection time buffers. Whereas at the bottom we can see all passengers flying back to Frankfurt, from which again some have booked onward connections via Frankfurt. If we now extract from this flowchart all the downstream cost driving elements, which I have marked as stars, with their respective buffer times until they would impact the airline, we can develop the individual cost functions as it is shown in this figure. Note here that the yellow curve includes all the cost for the first flight to Arlanda and the connexes there, whereas the red curve also contains the cost for the return flight to Frankfurt. Finally, the green function is the stochastic cost function, which includes buffer times and the deviations, the standard deviation of the block times on both flight legs, so that we can see this shift towards the right, which gives us more flexibility for the schedule recovery during the turnaround in Frankfurt. The sensitivity analysis of the recovery model was conducted in 3 scenario instances, one with the reference delay cost functions, one with the flight-specific but step-linear delay cost functions, and a third one with the stochastic cost functions. The arrival delay of all aircraft, as well as the passenger and crew connections, remained constant throughout all scenario instances, so that we only changed the arrival delay of aircraft 13, for which it was increasing in 5-minute intervals until the level of 70 minutes arrival delay. Then we compared the objective function, the delays for all aircraft, the applied optimal recovery decisions, and the sequence of outbound flights in Frankfurt. Here we see the objective function results, so the total cost of delay and schedule recovery for all 3 modeling instances. And we see that the total costs are lower when we have a model with step linear or stochastic delay cost functions, except for the case that the arrival delay of aircraft 13 exceeds 60 minutes and we have step linear delay cost functions. Because if we remember that there was a maintenance event scheduled after the flight cycle to Arlanda, the step linear cost functions consider this as a hard constraint and cancel the flight, the entire flight cycle, in order to have the aircraft back in time for the maintenance event in Frankfurt. To the contrary, if the stochastic model is involved with the stochastic delay cost functions, we consider also buffer times and in-flight compensation on the flight cycle, so that we have increased flexibility and we do not need to cancel this flight cycle and consider only a fraction of the total cost of this flight cancellation or the event that the aircraft would be back in Frankfurt for this maintenance event. And this is why we have lower total cost. Our key findings include that the average departure delay increases with step linear delay cost functions by 1 to 2 minutes in comparison to the reference delay cost model, and even more, up to 3 minutes with the stochastic delay cost model. Because now we consider the buffers and the in-flight compensation potential, which is comprised in downstream operations, and have additional flexibility for our turnaround recovery in Frankfurt. We can use this additional flexibility to maintain at least one more passenger transfer connection with the stochastic delay cost model. Further findings include shortcomings of the model with step linear delay cost functions, because we can see that the step linear cost functions are in some cases rather going in the direction that aircraft are delayed instead of using the available recovery resources. And on the other side, once we surpass such a threshold that the flight, for example, needs to be cancelled, then we have a dramatic change in the number of cancellations that need to be done in the rebuilding of the schedule. So we have to see how we can deal with this in the operational practice, because you know that the estimated arrival times are not so certain. They can change from one moment to the other, and then it's quite difficult how to handle such a dramatic change in the number of rebuilding and rebooking passengers. And we see that with the other models, we have not such a dramatic change. And finally, we have analyzed the sensitivity in the sequence of our outbound flights, which is relevant for the ATFM airline cooperation, as I've told you in the motivation, and proposed mechanism for this cooperation, such as the user-driven prioritization process, UDPP. For the model with the reference delay cost, we see that this model delivers rather fuzzy rankings, especially for flights with similar aircraft ready times, just because these flights have similar delay cost functions. For the model with step linear delay cost functions, this generates a very robust ranking until the cancellation of our flight when it has more inbound delay than 60 minutes, so that we see that the ranking remains entirely the same, except for the aircraft which has even more arrival delay, our causal aircraft. And finally, we see that with the stochastic delay cost functions, they are also robust until an arrival delay of 50 minutes, and afterwards the optimal ranking is not so certain anymore. So here we have to see, do we want to have rather a stable solution which always remains the same, or considering that an arrival time estimation is not always so clear and can change from 1 minute to the other, do we really want to know when the optimal ranking is not so certain any longer? It's just the preference needs to be clear. As a conclusion, I can tell you that stochastic delay cost functions can be applied to incorporate additional recovery flexibility comprised in downstream operations. When we applied our stochastic delay cost functions to a case study, this resulted in higher departure delay in comparison to a model with reference delay cost functions. Be careful here that the departure delay is still lower than the average inbound delay, meaning that we just used the flexibility where it is not critical, and with this we could reduce total cost by on average 12,000 euro because we maintained more passenger transfer connections and could even avoid the cancellation of a flight. Furthermore, we found out that a model with step linear cost functions delivers more robust solutions, but may, because of its hard constraints, may induce us with excessive cost and unnecessary schedule adaptations that we might not need if we would apply stochastic delay cost functions. Future work might go into the validation of the delay cost functions in further delay situations, also considering ATFM slots for all our flights. We could incorporate more sophisticated recovery options such as dynamic cost indexing and tail swaps. We could determine with our model the cost of schedule buffers for an airline, also the cost of uncertainty for a given flight plan. And finally, we could see how our schedule recovery solutions could be transferred into these priority values that the UDPP requires for the airline ATFM cooperation. And with this, I'm at the end of my presentation. Thank you for your attention, and I'm very happy to receive your feedback. Thank you.
Okay, thank you very much, Jan, for this very interesting work and very clear presentation. So you stick in your pre-listed presentation to 20 minutes. You start late because of a little bit problem at the beginning. So I think it is fair to have 10 minutes question and answer. So I would like to check the first question. So there is a question concerning the delay function. Could it be really linear? Do you have an answer for that?
Well, of course, it's not always linear from minute to minute, but we have to assume it to some extent, and to in order to give it into mixed integer linear programming, we need to have it linear, as the name says, linear programming. So we said 5-minute intervals is fine to have linear increasing, so because there's not so much change from 1 minute to the other, so that we can discretize it into 5-minute steps, and within these 5 minutes it's linear, and from one segment of 5 minutes to another segment of 5 minutes, then we have a change, so that we have different slopes in the increase of the delay cost there.
Yeah. Okay. Thank you. We can go to the second question. Same people asking. I'm not sure I really understand the question, because the question is, what is the relationship between inbound and outbound delays, and what is the role of aircraft turnaround time? So you explain us that you can use this time to recover. So perhaps you have something to add, Jan?
Yeah. Well, I mean, the difference that we really use is that most models are a little bit more high level, and then the turnaround is like just one block process and has a one process duration, so that we go a little bit deeper and we can see what are the interdependencies that cause this total duration of the turnaround, and where can we most efficiently cut some time off of individual processes in order to shorten the entire turnaround time, as I've shown with the turnaround network of the individual processes. So, I mean, if there's buffer inside, everything is fine. But if there's no buffer anymore and we have inbound delay, then we have to see which processes are the most efficient ones to recover.
Okay, thank you. I can see another question from the same auditor, so very active. Thank you, Milan. So the question is, how much delays are generated by airline scheduling, the urban spoke network, and how much ATC contributes to that? So I think you presented one of your first slides, and you show the different source of delay. So perhaps you can comment on that.
Well, as we've seen, it's more than 30% that the airlines generate and the airports generate during the ground time, and it's rather a lot of more than the ATFM regulations, which account for not even 10%. So we can see that the airlines have almost a triple effect on departure delays in comparison to what is generated by ATC and ATFM. Okay. That's why our focus.
Okay. So the next question, still the same author. Is this case realistic or scenario based, and was the stakeholder actually benefiting from this work? So this is a question I would like to ask you. What are the kind of the real application you have in mind? You show the case of Frankfurt, but still research. But do you have any idea of operational application?
Well, of course, we had to choose a case study, because such an analysis can only be done on a case study, according to my understanding. And it was just that we have the most accurate data availability in Frankfurt, but the methodology is very variable. We could apply it to any airport and to any hub airline in the world as soon as we have the data for them. And so in the end, the main customer or the main application would be inside an airline operations control center. It's really designed to be a decision support system for an airline in the airline operations control center. With the major location at the hub airport. Of course, you could also transition it into a low-cost airline, but there's not so many passenger connections inside a low-cost airline. So it's not so interesting, I would say, because there's not so many dependencies as I showed on the second slide. So there's entire network layer is missing because passengers need to take care of the transfer connections themselves. Yeah.
Okay, thank you. So the next question is about ATFM. So is prioritization by ATFM allowed? You will answer, but I think no. And under what conditions? So can you answer more precisely on that?
I'm not sure if I understand the.
Yeah, I think ATFM cannot prioritize flights. You said that in your presentation. All the flights should be equal.
Yes, exactly.
But,
yes.
So I think this is a strict rule. But okay, unless you have some other comment on that, we can go to the next question.
Yeah.
From George Mikonietti, do you make any assumption on the delay multiplicator impact for the flight with your stochastic approach? Can you answer that?
Well, the delay multiplier, first of all, is modeled with this inter-aircraft dependencies at the airport, so that if only one aircraft is delayed on the inbound, there are passenger and crew connections to others. So there's the first inter-aircraft dependency in there. And along the aircraft rotation itself, if it goes later into another airport and then has some interdependencies there, we have analyzed this based on data. So we have seen the flight cycle towards a destination and back. If the aircraft had 10-minute outbound delay, how long was the entire flight cycle? If it had 15-minute outbound delay, how long was the flight cycle on average? If it had 20-minute outbound delay, how long was the flight cycle? So we learned this delay multiplicator effect from the previous data of the summer season 2019 from our case study Airline.
Okay, thank you, Jan. There are still some questions, but I think we need to stop now. And I encourage you, Jan, to answer in the Q&A itself, and yeah. we'll have your answer. It will be very, very beneficial. Okay, so thank you again, Jan. So no applause because we are online. That's okay. This is I really appreciate your presentation and your answer. Thank you again.
Thank you.
Okay, so now let me introduce our second speaker, Hannes Brasso. He's traffic engineer and he has a focus on air traffic technology and is a research associate and PhD student in the same organization than Jan before, so the Institute of Aviation and Logistics in the Technical University of Dresden. His PhD objective is to develop a smart virtual barrier for airport operation based on the LiDAR object recognition system. So he also has some teaching activity related to safety, and Hannes will present his paper entitled Adaptive Point Sampling for LiDAR-based Detection and Tracking of fast-moving vehicles using the virtual airport environment. And so, Hannes, the floor is yours. And I think it's the previous presentation. So our director will switch off and play the video. Thank you.
Dear ladies and gentlemen, thank you for listening to this presentation. In this paper, we propose an adaptive point sampling strategy to detect and track non-cooperative, fast-moving objects of the apron in a labeled 3D LiDAR point cloud, thereby emphasizing taxiing aircraft. To that end, we exploit the virtual simulation environment introduced in our last publication to handle the generation of synthetic LiDAR scans of dynamic apron scenes. Today I would like to give you a short introduction to explain the need for improved surveillance and safety support of the airport apron, then give an overview of the overall approach before going on and discuss the main points. So, the simulation of the dynamic apron operation, the 3D mesh sampling, and the object detection and tracking method. Finally, I would like to present the results and give an outlook on further research. You all may know the statistics of Boeing. The interesting fact is that around 10% of aviation fatalities occur before an airplane leaves the ground. In addition, there are a considerable number of accidents and incidents with significant financial damage. Considering the SESAR objectives of increasing aviation safety by a factor of 10, the phase before takeoff seems to have a considerable risk reduction potential. Consequently, it is our goal to make airport apron operation safer using an advanced LiDAR sensor system. The overall goal of our project is to automatically detect and predict hazards at the airport using a LiDAR sensing system. The surveillance of the airport is usually ensured by a huge number of cameras, by radar, multilateration systems, or other surveillance systems. However, this information is usually not available in parallel, which becomes particularly clear when looking at the numerous camera angles. Besides, the resolution of some of these sensors, such as radar, is rather poor, and most of the sensor systems are practically blind to non-cooperative or smaller objects. In previous publications, we have shown that LiDAR sensors technology is a promising candidate to improve visibility at the airport and support the controller in his decision-making. LiDAR sensor technology has the advantage to create high-resolution 3D images of the scene and to derive movement parameters of the dynamic objects. Hence, using an advanced automation function, it is theoretically possible to predict movements and to consequently predict potential hazards. Only little work existing dealing with fast and accurate LiDAR semantic segmentation of such environments as like the airport. This is partly due to the fact that state-of-the-art algorithm in LiDAR semantic segmentation heavily rely on large-scale datasets with fine-grained label. In our last paper, we presented a methodology to generate simulated training data and to train or pre-train a model of semantic segmentation of a LiDAR point cloud in a virtual airport environment. Today, we will focus on the object tracking, and I will give you an outlook of the movement estimation. As I told before, in our last publication we proposed a simulation-based approach to generate synthetic training data of the Apron using a virtual airport environment that integrates a LiDAR sensor model. In this way, labeled 3D point clouds were sampled from a simulated Apron scene in a true-to-scale manner, which were then passed as an input to a state-of-the-art LiDAR semantic segmentation model. The proposed framework was readily generalized, able to different airports, operating scenarios, different static and dynamic objects, and sensor systems. In this way, we trained and tested successfully a LiDAR semantic segmentation model emphasizing on aircraft approach and leaving the gate, thin structures as like poles, airport buildings, and the ground plane. Our sensor at Dresden Airport has a so-called non-overlapping scan pattern. That means that the sensor is looking in another direction after each horizontal rotation. This has the advantage that the resolution is increasing with increasing time and fast smaller objects can be detected as well. However, moving objects are recorded disordered in the time stack. This is also called motion blur. On the right side you can see in the middle picture a time stack of a LiDAR scan over 10-second scanning time. During this time, the 3D model of the aircraft shown above as a snapshot moves further towards the sensor, which is positioned on the gate. During each horizontal movement of the sensor, the aircraft is located at another position, and due to the non-overlapping scan pattern, the aircraft is hit at a different position on its surface. At first, we do not really know whether these reflections are concentrated, for example, on the wing or the body, or equally distributed over the entire aircraft. For illustration, at this distance and orientation to the sensor, the aircraft surface is hit by approximately up to 30 light beams per sensor rotation, and the sensor rotates at about 36 horizontal resolutions per second. However, due to the scan pattern, it also happens that the aircraft is hit much less or not at all during a single sensor rotation. The question that now arises is, where exactly is the aircraft positioned within this blurry point cloud and how it is oriented? If you use, for example, only the last 20 points to calculate the position, it is possible that these represent only reflection points on the ring, for example. If you use the last 300 points, they may contain points from a previous position of the aircraft in the past. So what is the optimal number of points that best represent the current position of the aircraft? To answer this question, we have developed our adaptive point sampling strategy. In the following, I would like to explain the different packages of the framework shown on the left side. Before we are able to test our system in the real world, we first want to investigate the question with the help of our simulation environment. Accurate, true-to-scale 3D modeling of the airport environment is a key building block to simulate realistic apron operation. To that end, we construct a 3D model of Dresden Airport as illustrated in the figure. In addition to the static components of the airport infrastructure, apron operations involve a large variety of movable objects, including aircraft, ground vehicles, and others. For the first implementation of our tracking algorithm, we restrict the set of movable objects to the most important category, aircraft, which is represented by an A320. However, the presented method is generalizable and can be applied to any other dynamic object as well. The virtual environment depicted in this figure show an arriving A320 instance and subsequent positions to demonstrate the motion pattern of an aircraft selected in our experiment. The large green circle indicates the range of the LiDAR sensor located on the northeast rooftop of the terminal building at Dresden Airport, as indicated by the green color cone. We have simulated all potential inbound tracks at Dresden Airport and several runs with varying speeds. The maximum speed in the curve and straight segments was specified in each run, and the actual speed were diced in accordance with the underlying kinematic models. To overcome the challenge of motion blur, we first measured how sensitive the detection performance is towards varying velocities of the aircraft maneuvering along all permissible inbound tracks. Notice that the insight gained from this analysis helps to understand how the motion, the relative location, and the orientation of the aircraft affects the scanning behavior of the LiDAR, and to derive a point sampling strategy to detect and track. This results in the following track starting from the roll-in points in the sensor range A, B, and C to all A320 parking positions at Dresden Airport. The taxi lines were not always exactly followed by the aircraft to simulate a realistic run. The ground truth position, orientation, and velocity were stored for every simulation run and every time step. Simulated scenes were then scanned by our LiDAR simulation module. The LiDAR sensor at our disposal is a first-generation Opal 360 high-performance sensor developed by the company Naptec. The sensor operates with a laser wavelength of 1540 nanometers and provides a field of view of 360 degrees horizontally and 45 degrees vertically. Assuming a scanning duration of 2 minutes and provided that the sensor operates with a pulse repetition rate of 200,000 kHz, the LiDAR sensor forms a point cloud of the scene containing up to 24 million points. Each of these points is defined by XYZ coordinates and its intensity values. The top figure illustrates how the scan pattern evolves over time. The red dot represents the sensor position. Here you can see the idea behind this non-overlapping scan pattern as it increased the resolution over the time. The developed sensor model contains the parameters shown on the left side. If you are interested in more detail, please check out our last paper. The result is a simulated point cloud as briefly shown in the beginning of the slides. On the left side you can see a stationary aircraft which was scanned by the sensor model over 10 seconds, nearly at the same position as the moving aircraft on the right hand side. The resolution of the aircraft is increasing over time. The actual position of the aircraft is obvious, since the aircraft is represented in very high resolution. On the right side you see a moving aircraft, which is also scanned over 10 seconds. The static objects of the scene, so the buildings for example, are very well resolved because they do not change their position to the sensor within the scanning time. However, the aircraft appears as a blurry point cloud as it changed position and orientation over the time. Here it is much more difficult to tell where the aircraft is actually located. Each of the illustrated points has a timestamp. However, the most recent points do not have to be those that best represent position. For example, it may be that the rear part of the aircraft was captured last. For each simulated aircraft movement, we searched for the number of historical points that best represent the position of the aircraft. Thereby we found two respectively free correlation, which do not seem surprising. If the aircraft is closer to the sensor, the more historical reflection points must be collected to best represent the position of the aircraft. Due to the spherical pattern of the sensor, the number of points in a specific area during a specific time interval decrease with the distance to the sensor. Nearby objects are captured by more light rays in the same time interval than more distant objects of the same size. The second correlation results from the speed of the object. The slower an object moves, the more points should be used to calculate the position. Stationary objects should be scanned as long as practically possible to best represent the surface of the object. For fast objects, only a few points should be used to calculate the current position because the position of the aircraft moves continuously while scanning the required amount of points. A third correlation results from the orientation of the aircraft to the sensor. By changing the relative orientation, the reflective surface of the aircraft changes. However, our inbound tracks have not given sufficient variation of the orientation. Some angles were strongly influenced by other effects such as self-occlusion on the parking position. Therefore, no sufficient correlation could be derived. However, we want to address this problem by generating further test data in the future. On the right side, you can see the resulting optimal number of historical points depending on the object distance and object speed. In our simulation, we have assumed velocities between 0 and 16 meters per second. The unrepresented velocity and distance combinations were then interpolated from the data. We then coupled this adaptive point selection strategy with a Kalman filter to smooth the results, make them less sensitive to, for example, occlusions, and thus make the results more robust. In each time step, the previous object distance to the sensor and the previous object speed is used as an input for selecting the optimum number of historical points which represent best the actual object position. The measured position is used as an input for the standard Kalman filter to calculate the corrected current position using the previous Kalman prediction. The corrected current position is then used to calculate the current speed and distance to the sensor for selecting the correct number of LiDAR points in the next time step, and so on. In that figure, you can see a snapshot of a dynamic scene of a rolling A320. The aircraft is detected by the blurry point cloud and tracked using the adaptive point selection strategy and the standard Kalman filter. In the figure below, you can see the detected bounding box and orientation as well as the measured speed in blue. In green, you see the true position and orientation of the aircraft. In the upper right corner, you can see the measured positions qualitatively compared to the actual positions of the aircraft in the top view, also indicated by blue and green. The measured position and orientation is represented by the standard bounding box, as you can see in here in the zoom in. In addition, the direction of the movement is indicated by an arrow, as you can see on the right hand side. The measured speed is displayed near the bounding box, as you can see also in the picture. It is 7.46 meters per second in that test case, and we have tested this method for 500 inbound tracks in discrete time steps of 0.1 second. We determined the position, the orientation, the speed of the aircraft and compared it with the real values at the same time. We measured the position arrow, the orientation arrow, and the velocity arrow, depending on the object distance and speed, which is shown on the next slide. This resulted in these illustration exemplars shown by the position arrow. The position arrow was calculated between the bounding box centers of the measured and the true bounding boxes on the ground. It can be seen that with only one sensor placed on a terminal building, the developed framework works quite well over all speeds and distances up to 350 meters with a position error of about 5 to 10 meters in our simulation environment. In the white areas, there are no or not sufficient measurement data pairs available. There are single outlier clusters associated with certain parking positions or initialization error. As you can see, for example, at the distances of 100 and 250 meter and low speed of 0 to 3 meter per second, here the localization error is quite high. The reason for this becomes obvious when you look at the measuring points in a simulation environment. You can see all measured position over all inbound tracks in bird's eye view. The measurements are colored by their position arrow. The sensor is located on the rooftop of the gate in 00 marked by number 1. The two large measurement arrows described before are also found here. The lower left arrow is caused by a passenger boarding bridge which hides a large part of the front-on aircraft. The upper arrow on the last slide is shown in the right box caused by self-occlusion of the front-end part of the aircraft, therefore the position is always assumed to be far in the back. Another but not very surprising conclusion is that the cross-track arrow and the long-track arrow are strongly influenced by the orientation of the aircraft towards the sensor. This knowledge can be used, for example, to place an additional sensor to achieve the desired accuracy. For example, we can assume that by placing a sensor in 2, it will reduce the cross-track arrow at x 150 meter. Our further research currently deals with the quantitative motion prediction of detected and tracked objects. First results of quantitative motion prediction are shown in here. All possible future aircraft positions are shown based on the kinematic behavior of the detected aircraft, including the structure of the taxi lines. The probability of the future motion state is represented by its color. And these motion predictions shall be used to predict potential hazards as like collisions or runway incursions. If you're interested in our work, if you have any questions, suggestions, or wishes for a cooperation, please do not hesitate to contact us. We are looking forward for interesting conversations. Thank you very much for your attention.
Okay, thank you, Hannes, for this very clear again and very interesting presentation. So, especially for me, because my first research topic was dedicated to LiDAR, so I'm really still a big fan of that. We can move to the question now. So theoretically we have only 3 minutes, but it will not be fair. So we'll try to have the 10 minutes we are supposed to be allowed to spend on that. So I can see a question by Milan. It's about the benefits of the LiDAR measurement on the airport. Is it improvement of efficiency of ground movement, reduce the risk, prevent accidents? So who can actually benefit from this work? And can you answer on that, Hannes?
Of course. Thank you for the question. The biggest benefit of measuring or semantic segmentation of the airport apron using a LiDAR sensing system might be that you also detect the non-cooperative objects which are nearly operating blind in today's environment. So the operator, the apron controller do not know where, for example, ground vehicles are placed. By using this semantic segmentation and the LiDAR sensing system, it is possible to present each position of every moving object or static object of the airport apron to the controller or any other person who is interested in that information. Another thing is, because he's writing something about reduced risk, of course, one of these goals is also that we want to predict the movement of each movable objects on the airport apron to calculate, for example, collision risk in the near future, like 10 seconds, 15 seconds, whatever. We need to investigate this so that the controller can automatically detect potential collision risk or, for example, runway incursion risk of the whole environment at the same time.
Okay, very good answer, Anne. Perhaps I cannot see any other question in the list, but I have some. I will take this opportunity. Perhaps to go a little bit further than the previous question, my question would be, what is really the LiDAR added value compared to a stereo vision system? I mean, in the surveillance task, we can detect the object, the position, the velocity. We can also do that with 3D vision system. So what is the real benefit of the LiDAR system?
Yes, you're absolutely right. First thing is that you, using a LiDAR sensing system, you measure distances. So using a visual system based on video, it is always not a real measurement. You have always to project distances in a two-dimensional environment. But the main case is that you can easily combine multiple LiDAR sensing systems over the entire environment and combine these 3D points together to one 3D environment. So it's pretty easy to handle multiple sensors, and if you're having a look on that stereo vision measurement, you always stay at that point that you have multiple viewing angles which need to be controlled by the controller itself.
Yeah, okay, I agree. I have a question in the audience from Sebastian. Is LiDAR affected somehow by fog or low visibility scenarios?
So if you're really interested in that point, we have some other publications about that. It depends on, of course, on the wavelength of the sensor. We have something like 1540 nanometer, which is nearly twice the one for visible light, which is anywhere between 360 to 80 nanometers. This has some effects on the light, of course. In general, bigger wavelength means it is not that affected by smaller particles, but at least we have some higher absorption function by water particles. Currently, we are running some tests of rain scenarios, measuring the effect of fail reflections and so on. But in general, the LiDAR technique is going big steps, and there are some very promising results from other universities which measured object detection in foggy scenarios, and they were able to extend the vision of the human by the factor of 10 using LiDAR sensor system. And they do it by not having a look on the first reflection of the light beam, which is reflected by some particle in the atmosphere. They wait until the light beam is reflected by the object of interest and have a look on that. So they calculate the distance to that object using the third or the fourth reflection of the specific light beam. So to conclude, this is still a problem of LiDAR sensing, but they're doing really good job in that specific area so far.
Yeah, okay. Thank you, Hannes. I think another question from the audience from Konstantinos is about more or less about the same question. Not really, not exactly, because the question is about in during rainy season or rainy conditions, there is some reflection on the water on the tarmac. So would it be some error for the lidar due to that?
Yes, as I told you, this is actually under investigation, but we had some primary measurements a couple of years before. And as I told you, when it came to wet surfaces, the absorption of that water is increasing a bit, so you don't have these strong reflections anymore. But yeah, as I told you, this is under investigation right now, so I can't answer it in more detail. I'm sorry.
I will thank you, Ernest, again. I will have the privilege to ask the last question. So my question is about real life experiments. Do you have scheduled some in the airport to fully validate your approach?
Yes, we do have that sensor placed at Dresden Airport, which we are simulating. So we stored a lot of sensor data and working with this data in our simulation approach. The next step will be, of course, to go to airport again using our semantic segmentation approach and the tracking approach itself. The problem is to learn these data further with real data, as it needs the hand-labeled annotation of these data, which is very cumbersome. So you have to label thousands of points. So as I told you, 200,000 points per second, and you need a lot of training data to overcome the real scenario. So we'll see how good the pre-trained system on the simulation environment works on the real data. But when it came to hand annotation of the real data, we might came to that point that it is increasing too much, that problem, I would say.
Yeah, okay. Thank you, Hannes. So same like Jan, I encourage you to perhaps to complement your answer in the Q&A, and I think it would be useful for everybody. So I would like to thank you first, our presenter, Jan and Hannes. So thank you so much for your presentation and also the clarity of your answers to questions. So it's very good. And also like to thank the audience because it was quite active. I'm not used to do that, to chair a session like this in teleconference, but it's very active. So I would like to thank everybody. I would like to say to wave also to my friends there. I can see some in the attendees, and so thank you. And I think we have another part of the program now, which is the networking. So thank you to everybody, and bye bye. So thanks again, Jan and Alice.
Thank you. Bye bye.
Bye bye.
The use of drones is becoming more and more important in air transport, employing wide parts of our skies. Drones operations are expected to take place and be integrated in all the airspace segments. A peculiar part of our sky is represented by the airspace classes Delta and Golf, where separation is delegated to the pilots and many different airspace users are already present. If you want to know how Eurocleared tries to face this challenge, come talk to us at our webinar, have a look at our poster, and watch our full video.